So we've been looking at geometric sequences. We've been looking at patterns of repeated multiplication where we multiply by the same number, the common ratio, every single time. Building off of that, we're going to deal with exponential functions, which have that same kind of pattern of repeated multiplication. So our general equation is going to look like y equals a times b to the x. And I'll break down what those letters mean. I would say a lot of the time you'll see people write it with the parentheses, but sometimes they might also, you may see it written this way. You might see y equals a times b. So you might see the multiplication symbol in there, or you might see parentheses. Either way, there's two important pieces of information we need. We need a, which is your initial value. So think your starting number, starting at 0, your 0th term. That value is your y-intercept still, just like when we did, your initial value was always on the y-axis if you're looking at a graph. So same idea as linear equations. The b here, I'm going to call a growth or decay rate. And that is going to have the same idea as the common ratio. It's whatever it is you're multiplying by each time to make your pattern. And then one important thing to notice is that the x in my equation has to go up in the exponent. And the reason it has to go up there is because we're doing a pattern that is repeated multiplication. And the way we represent repeated multiplication is with an exponent. So that's why these are called exponential functions. Your variable is up in the exponent. Couple things to note with your b value. If your b value is greater than 1, or common ratio is greater than 1, same idea, you're going to be having something that we call growth. So think about it. If you're multiplying by 2 or by 3 or by 1.5, your numbers will be growing or increasing. Sorry, I started to get ahead of myself. You'll see an increase in your numbers. When we deal with exponential functions, we don't typically deal with a negative number that we're multiplying by. We do that in sequences, but not so much in exponential functions. But if you have a fraction that is between 0 and 1, so like 1/2 or 1/3 or a fourth or whatever, you're going to have what we call decay, which just means that you're decreasing your numbers. So it's going to be very important when we get to kind of the second half of our notes. So let's jump right in with some examples. There's kind of two types that happen. Sometimes you're given a growth factor or a rate at which you're growing just as kind of a phrase. So in this first example, it says the initial value, and number 1 is 5, and it's something that doubles. So if our initial value is 5, that means we're using a equals 5. And doubling, we know, means times 2. So it's going to be as simple as saying that my b value is 2. That's what we're multiplying by. And this is why when we were doing sequences, we didn't want you to write anything as division, because every single thing for these equations is written as multiplication no matter what. So in writing your answer, you would write y equals 5 times 2 to the x power. Make it very clear that the x is in the exponent, not just being multiplied with the 2. All right, second example. It says initial value is 4. So right off the bat, I know a is 4. And then this one says it halves. It's halving every time, which means I am multiplying by 1/2. We know halving means we're dividing by 2, but again, we write it only as multiplication. So we multiply by 1/2 each time. Let me say y equals 4 times 1/2 to the x power. So if you've got the hang of this, pause and try number 3, and then turn it back on when you're ready to check your answer. In this one, our initial value is 7, so a equals 7. And it is tripling. Tripling means times 3, so b equals 3. So then our equation would be y equals 7 times 3 to the x power. So those are pretty straightforward. Not a lot of extra thinking. As long as you know your initial value and what your pattern is doing, I think those are pretty straightforward to write. Where things maybe get a little bit trickier is when you're given a percent. Still not terrible, but percents are really useful because a lot of real world exponential growth and decay happens based on percents. So we want to make sure we can work with those as well. Initial value stays the same when you're given a percent. The thing that gets a little bit different is going to be your B value. You have to do a little bit of math to get your B value. So if you are given a percent and you need to find what B is, you've got to think about a couple different things. First, you need to think about is, do you have an example of something that should be increasing or should it be decreasing? If it should be increasing, you would take, to find your B value, you would take your percent and add it to 100, whatever percent you were given. And that's going to give you a B value over 1 is ultimately what we're trying to create so that we make sure our equation is actually growing. Once you get that percent, we're going to convert it to a decimal, and I will remind you how to do that. You've probably learned how to do it in middle school, but I'll remind you how to do it in just a minute. So we're going to convert it to a decimal, and they're no different. The decimal and the percent are exactly the same representation, but our equation is based on kind of a decimal form, not using the actual percent symbol values. If we're decreasing, similar process, we're going to do 100 minus the percent. And then we would still convert it to a decimal. So I think that's kind of easy to remember. If you can remember that you either need to add it to 100 or subtract it for 100. The increasing, when it's going up, is the adding, so that should make sense. The decreasing, when it's going down, is a subtraction. So that's a helpful way to remember that. I like the problems at the bottom to start with here, actually. So I'm going to jump down to example 8, and then we'll come back to these. So if you printed out your notes, I'm going to jump around just a little bit. Look at number 8 for me, way down here. So in this problem, we're told that we have a starting amount of 14. So right off the bat, A is 14. And then we're told we have a 20% increase. So this is where we have to do a little bit of work. It's increasing, so I'm going to use my rule we wrote up here that says to find the B value, we need to add our percent to 100. So B equals 100 plus 20, which is 120%. But we can't take that 120 and put it right into our equation because our equation doesn't use percent symbols. It's going to be based on a decimal. So to do that conversion, I'm going to take my 120%. And to convert it to a decimal, technically the math that we're doing is we divide by 100. What I'm going to do is show you a shortcut. To divide by 100, if there is no decimal already built into your percent, put it at the end. And the shortcut would be to move it 2 to the left. So that is the same as 1.20, but when we have a 0 on the end, a lot of times we take that off. You might not see that 0 there. Zeros on the end can be dropped off if they're after a decimal point. So 120% is the same as writing that we're going to multiply by 1.2 over and over again. It's an increase here because now my B value is greater than 1. That's why I had to add that 100 in there. It accounts for keeping what you started with and adding the 20%. So then in writing your equation, we write y equals 14 times 1.2 to the x power. And that's my equation. In number 9, we have a starting amount of 500, so A equals 500. And again, we've got to find B because they told me I have a 7% decrease. So when it's a decrease, we're going to do 100 minus 7, minus your percent, which gives me 93%. And the reason we do that math is we're accounting really in our equation for how much of our initial value we keep. So in example number 8, for example, we keep all of what we started with and add 20% to make it grow. In this example, if we're losing 7% every time, we're keeping 93. So that will keep our value below 1, so that when we're multiplying by 93%, once we convert it to a decimal, it will give us the correct decay pattern. So if we have 93%, again, technically you're dividing by 100. Shortcut would be to put a decimal at the end if there is no decimal in the percent already, and move it 2 to the left. So that is the same, 93% is the same as 0.93. So to write our equation, we would write y equals 500 times 0.93 to the x power. So if you're feeling good, I want you to pause, try number 10, and then turn your camera back on when you're ready to check your work. In number 10, we've got a starting amount of 250 and a 12% increase. So increase means I'm going to add it to 100. So 100 plus 12 is 112%. And then we convert to a decimal. So 112% as a decimal. Divide by 100. Move your decimal 2 to the left. Is going to be the same as 1.12. So our equation would be y equals 250 times 1.12 to the x power. So now let's go back and revisit numbers 4, 5, and 6. Now that you've seen how the equations are created, let's actually analyze the equations ourselves. So these examples, our directions say identify as an increase or decrease, find the initial amount and the percent change. So in number 4, when I'm looking to decide if it's a percent increase or decrease, I'm checking out right here, looking at my b value. And if it's lower than 1, it's decrease, bigger than 1, increase. So in this case, 0.82 is less than 1. So this one is going to be a decrease or a decay. So then we know the initial amount is the number out front, not next to the exponent. So our initial amount is 10. And now we have to figure out the percent change. So since we know this was decreasing, and the way we found this value was doing 100 minus the original percent, we can actually use kind of reverse logic there. And we can do 100. Actually, let me say this first. We can take 82, 0.82. And if I want to make that a percent, I would move my decimal 2 to the right. I would go backwards, and 0.82 is the same as 82%. So to find my percent change, we didn't decrease by 82%. Remember, to get that number, we had to do 100 minus whatever the percent we were given was. So I'm going to do reverse logic here. I'm going to do 100 minus 82, which is 18. So we had a decrease of 18%, meaning that we kept 82%. Let's try another one. In number 5, it says y equals 3 times 1.15 to the x. So first thing I'm checking out is the number right next to my exponent in my parentheses, which says 1.15. That is bigger than 1. So this one's going to be an increase. And my initial value, pretty quick to pick out, is the number out in front, which is 3. So 1.15 is something that I'm going to first convert back to a percent. So 1.15, I move my decimal 2 to the right, which is the same as multiplying by 100. And that would give me 115%. But we didn't actually grow by a whole 115%. We kept what we started with. We kept the 100%. And then we grew whatever extra there is. So for these, if you're increasing, we want to do the percent that we have minus 100. So backwards from the other example. These, I think, are the trickiest problems. And that would tell us that we had a 15% growth. If you're feeling good, and this is kind of making sense to you, try 6 and 7, and then turn your video back on, pause your video, turn it back on when you're ready to check. In number 6, this one's kind of interesting. In number 6, there's a 2.5 in my equation as my b value. So I know that's an increase. That is certainly bigger than 1. I can quickly identify my initial value as a number not next to the exponent, which is 8 in this example. So here we had 2.5, right? 2.5. If I convert it to a percent, I'm going to move my decimal 1, 2. And notice I ran out of places there. So 2.5, I have to add an extra 0 at the end, is the same as 250%. But again, since it was increasing, we didn't grow 250%. We kept 100 and grew the extra. So I'm going to do 250 minus 100 is 150%. So we had an increase of 150% here. All right, last one, we've got y equals 100 times 0.5 to the x. 0.5, my number in the parentheses, is less than 1, so I know this is a decrease. I know my initial, that 100 out front, my initial tells me that I started with 100. So I'm going to take my b value, 0.5, and I need to convert it back to a percent. So I move 2 to the right. And again, I ran out of spaces, so I have to put that extra 0. That's going to be the same as 50%. That's probably one you know off the top of your head. 0.5 is 50%. And then I need to do 100 minus 50, which shows me that we did have a decrease of 50%. So that's a quick overview of kind of the basics of exponential functions. Make sure you come to class so you get some extra practice with these, and then we'll have another day with some actual word problems and some really practical applications tomorrow.